Yeah, thank you for the introduction. As I said, my name is Sjoerd Hengeveld. I'm from Eindhoven University of Technology. And in the coming 12 minutes, I would like to give you an overview of the experimental work I did in the last half a year. So the presentation is titled Mixed Mode Fracture Toughness of R260MN Rail Steel using Compact Tension Shear Specimens. And so it is about rails. It's about rail steel. And it's about fracture in rails. And in rails, we talk about a multi-axial loading. We have the vertical axis. We have the vertical loading due to the wheel axles. We have the horizontal traction force. We have a lateral force, any residual stresses, any thermal stresses. So it's a multi-axial problem, which leads to rolling contact fatigue. And on the top left figure, if I have a pointer, yeah, on the top left figure, you see an example from practice. So this crack on top is a so-called squat defect, which is a inclined crack from the head of the rail. And this vertical fracture surface that was done in the lab, there was this rail fracture to be able to see the fatigue crack from practice. So as we know, the total fatigue life consists of 3 phases. We have an initiation phase, a stable crack growth propagation phase, and we have final fracture. And in the current presentation, I will focus on the final fracture phase. During the presentation, you can see at the bottom of the slide an overview of where we are. So first, I would like to explain you the methodology. So my methodology of doing these fracture tests has 3 phases. First, I'm doing the pre-cracking phase. So we have made, sorry, we'll also introduce these first. So I'm using, as introduced on the first slide, I'm using R260MN rail steel, which is a commonly used steel in the Netherlands and all over Europe. And we have used rail. So the specimens I have are made of the remainders of the picture you saw in the previous slide. And we make so-called compact shear tension specimens out of the head of the rail, because that's the place where these squats, these fatigue cracks in practice occur. So here a schematization of this specimen, but I will come back to that in a second. So this setup, this compact tension specimens were developed by Richard in 1981, and you see here a picture of the setup. It exists of the specimen in the middle with 2 grips, and it's loading in a hydraulic machine, so a vertical load applied. But because you can change the orientation using these 7 holes, you change the mode mixity between a pure mode 1 test and a shear test. So the solution depends on the load angle alpha, or that's how I call it in this slide. So we have 7 discrete angles, and then there are analytical solutions available to calculate what the stress intensity field is depending on this angle. So let me first go to that. So what you see in this graph is on the horizontal axis, this applied load angle, and on the vertical axis, the normalized stress intensity factor K. So this is the K1 component. So for alpha equals to 0, which corresponds to a pure mode 1 test, your K1 is maximum, and it diminishes when you go to a pure mode 2 test corresponding to alpha is 90 degrees. This would be the corresponding mode 2 component. And finally, we have an equivalent stress intensity factor, which we use to evaluate our fracture results. And this equivalence is based on literature, also developed by Richard. And you see there is a material constant C, which is often taken 1.155 for steels, which corresponds then to a more or less von Mises equivalent stress principle. These analytical solutions for the stress intensity factors are obtained also from literature, but also made my own finite element models to validate those. So then I'll come to my methodology, which exists of 3 phases. And the first phase is the pre-cracking phase. So we have the specimen, which has an initial notch made by electrical discharge machining. And using the pre-cracking phase, which is a cyclic loading phase in mode 1, pure mode 1, I try to get a pre-crack of approximately 1 to 2 millimeters. And these tests are done at room temperature. Then we do in mixed mode, so under a specific load angle alpha. I'm doing a test up to a relatively low load level, so definitely below fracture, more or less in the same region as the pre-crack load. And we do this to be able to use the digital image correlation to look at the local stress strain field as already been introduced in some of the earlier presentations. And finally, we do the fracture phase, which is also in mixed mode. So also depending on the load angle, but we do this at -5 degrees Celsius. And for this, we cool down both the specimen and the grips in a fridge up to approximately -40. Then we transfer everything to the hydraulic machine, wait up till it's at approximately -5 by monitoring it with some thermocouples, and then we do the fracture test. And because you have, due to these low temperatures, you then have condensation on your surface, and that's the reason we cannot use the DSC anymore in this phase. That's why we split it in these two aspects. So that brings me a bit to the results. So what you see in this graph is a pure mode 1 test. So on the horizontal axis, you have the clip displacement, which measures the opening of the crack mouth. And on the vertical axis, you have the applied load. This blue curve is the experimental results of the fracture test. Then we can make a fit through it through the linear regime. You can make a fit according, which is normally also done in the standard, for example, the ACM E647. And then you can distinguish more or less 3 phases. So we have this first phase, which is in which you can see that the load comes over the crack opening load. So that's where this change in slope comes from. Then we have this second linear phase in which the load increases and linear with the crack opening displacement. And then suddenly we have the third phase, which is here governed by this pop-in behavior. So that's a small unstable crack growth, after which it arrests again, and then you, by keep increasing the load, it will finally lead to final fracture. And so we have a Fmax, the maximum load to fracture. And in my research, I'm evaluating all these tests based on this final maximum load of fracture, not taking into account these pop-ins. That's also because we're doing mixed mode tests in which and the criteria which is used, for example, the X6470 is developed for mode 1 test. And I'm in the end want to use these to predict the failure load of these real squat defects, but I will come back to that. So as I said, I evaluate the stress intensity factors as the maximum load, and we can plot them in a graph like this. So on the horizontal axis, you'll find the applied load angle. On the vertical axis, the applied or the stress intensity factors. And these are the K1 max values. So the K1 values corresponding to F max, to the applied fracture load for the different angles. We have the K2, which increases with increasing crack length. These are based on analytical solutions. And we have the K equivalent. And initially, before we started this research, I thought that evaluating this based on K equivalent would be would result in the best fit. But if you look now, so this yellow line is the average of the K equivalent, and the dashed lines are plus and min -1 times the standard deviation. And we have the similar line for K1. So it turns out that for these specimens, the specimens for this type of steel, R260MN real steel, evaluating the fracture condition based on K1 max yields better results. Then we have the corresponding crack paths. So what you see in these 4 pictures are 4 tests corresponding to 0 up to 45 degrees. Obviously, when we have a pure mode 1 test, we will have a straight crack, which was also expected. And then with increasing crack or applied loading angle, we get a deviating crack path. It's also interesting to see that, especially at these higher crack paths, it's also not a straight line. So there's a slight curve in this crack path. Then, as I introduced in the beginning, we use used rail, and these I had 13 specimens in total, coming from 3 rails from practice, fabricated between 1990 and 2010. And with these lines, you see the mean average K1 max for the 3 different rails. And you do see that there is one of the rails has a lower mean fracture toughness. All rails have approximately the same coefficient of variation between 0.1 and 0.12. And as I introduced, so these were the results based on the fracture test, but we also did the digital image correlation test as already introduced in previous presentations. So the digital image correlation setup exists of two cameras, which simultaneously both take a picture. And using these pictures, if you combine them, you can combine them into a single grid, and then you can calculate all kinds of displacements and strains. And using the maximum principal strain, we can get an indication from where the real crack tip is, because there will be a jump in your in the calculated principal strains. So if we zoom in a bit, we have this area in which there was no correlation on the top left. That was the initial notch made, and then we have this area with a high maximum principal strain, and this is the pre-crack length. And if we qualitatively look at the orientation of the maximum principal strains, which is a bit hard, but that is indicated with these lines. And as also indicated in one of the earlier presentations, there are a lot of knobs which you can turn in this DSC evaluation depending on your facet size, depending on your resolution. But qualitatively speaking, this is more or less the direction perpendicular to your maximum principal strain. And that corresponded for this test to the final crack path. But this is something I'm looking into more. Other applications for the digital image correlation are calculating stress intensity factors, for example, or use it as a virtual extensometer, because the normal extensometer added is only able to calculate crack opening displacements, because it's added to the specimen itself, and the crack sliding displacements are not captured by that. But using the DSC, we can decouple these. This brings me to the final conclusions. So K1 max gives a smaller scatter than K equivalent in evaluating the final fracture for R260MN. The fracture toughness, the maximum fracture toughness, is batch dependent. And the crack growth paths are consistent with the maximum principal strain direction. And then one last slide of an outlook of a bit look forward. So as you saw in the first slide, we had this squat effect from practice, which was broken. That was broken in the 4-point bending test. And the final goal is now to recalculate the fracture load of this 4-point bending test, including the real squat geometry. So I'm using a 3D scan to model that. And I made a finite element model of this test. And in the end, we're going to expand it to calculate the residual fatigue life of squat effects. Thank you for your attention. It was a brief summary, so I'm more than happy to answer any questions or have further discussion.